Good afternoon. In the last lecture, we talked about different ways of generating security assertion. Then we talked about that we need to generate tests to ensure that generated assertions are valid. Now, I am going to talk about once you have used this assertion for pre-silicon validation, should we just forget about them or there is some more utilization. I am going to talk about two utilization scenarios that many industries use, but most industries basically stops here. They basically for functionality as well as for security vulnerabilities, they primarily use it for pre-silicon validation.
So, I have one question. So, whatever assertions you have generated, what is the way you can guarantee that I have generated good enough assertions?
Very interesting question. So, whether it assertions or whether it is properties, it is basically undecidable problem that it covers the design completely. All it guarantees, if you have a coverage model, let us say line coverage, statement coverage, branch coverage, only from that perspective we can guarantee. But if we are trying to see, well, I generated 300 security assertion, does it cover all possible security vulnerabilities? Is it completely protected? Answer is no, there is no such guarantee, and same argument applies for functional assertions also. Even if you generate assertion or even if formal verification domain you have 3000 properties you checked, you can never say that my design is completely functionally correct, you cannot say. Only thing you can say, the properties I checked, my design is guaranteed to be correct for those properties.
So, then what is the kind of procedure followed in the industry on writing enough properties thing? So, formal method ensure that if the property is there and the design in no circumstances that violates that. So, that way it is good, but if I do not have enough properties, then I do not verify the circuit properly, right?
Right. So, let me talk about functional domain, then we will come to security domain. In functional domain, the idea is whoever is the verification manager, most likely the people who are professors like me, our PhD student, they sat and they write something called test plan. They develop the scenarios that need to be checked, and where does they come this scenario? They look at the architectural or whatever the design specification, and they kind of say, well, this design is supposed to do banking transaction, it should allow customers to withdraw money, it allow customer to check their balance, it allow customers to deposit money, whatever is spelled out, most likely each of that statement would be an entry bulleted list in that test plan. So, then question becomes, for each of those scenarios, do we do a test generation and check it? Do we put an assertion for it? Do we formally verify it? But the starting point is test plan, and test plan does not guarantee anything. For rest of the company, the test plan developed by that verification manager is the golden thing. That does not mean anything, but it is better than having nothing. People are just randomly checking whatever they want to. Based on the original document, they develop a test plan, and then rest of the people in the verification team trying to make sure the part of the test, and test plan may include a sentence like we need to have 100% statement coverage, we understand the branch coverage would be 98%, we understand the transition or state coverage would be 80%. So, they put a bar, they do not put, well, path coverage would be 100%, you can't do path coverage 100% any reasonable size hardware design. Software design it may be possible, because there are exponential number of paths, there is no way you can check all of them, right. So, test plan is the starting point, state plan is the golden thing. How do we know that test plan is complete? That is a different story. So, now I am going to talk about two scenarios. Let us start with the so when you have this, let me go straight to the, let me go to the picture, then I come back to this one. Where is the picture? So, basically whatever we have gone through in the assertion, the question is, do we select a subset of the assertion and then we use it for dynamic refinement while the chip is in deployment, it is inside a device, somebody using the device. So, we are going to look at this two story, assertion selection and assertion refinement, but before we go there, the question is, ideally I would like to take all those millions of assertions and push it to the post silicon. so that in the device it is there. But the problem is each of them is like a function. Think of it as a function you wrote and you want that function to be in assembly. All these assertions is nothing but a function call, and that function call would be sitting in the assembly. That is going to be lot of assembly code, lot of overhead in terms of code size, power dissipation and all that stuff. So, then that is why that overhead may be even hardware, it could be lot of area, power, performance penalty. So, then objective is one option is do not keep any of them, get rid of them, and the way people get rid of them is by doing simply this. So, what they do is basically they do hash define, you add this sentence on top of your file when you are done with your, and it is basically the comment line or whatever it is. So, then that assertion call, all of the assertion call is basically become a comment, and when you compile, compiler will get rid of it, it is gone. You do not have to manually go and delete them, right. But as I said, this would be a easier solution, but you may want to keep some of them to keep the guarantees even if you formally verified. So, the one other thing industry does is that this is my test plan, or this is the, let us call it test plan or whatever, verification plan. In that plan, if I want to do a Venn diagram, out of this plan through my formal simulation whatever it is, I am able to check this part, right. Sorry, I am able to check, I am done with this part, this is done, but this part is still not done. For whatever reason you could not verify it, you could not check it, those assertions companies want to keep. At least safety critical system, that is how it is done. If you want to check 10 properties, 8 of them you can formally verify, good. The 2 you could not verify, you want to keep them in the design. Otherwise, the safety critical requirements is not met. If any time anywhere the problem happens, you at least know immediately. Now, then the next question is, if I want to keep some of them, which of them and what can we do. So, here is some study I wanted to show you. So, basically obvious story would be, if you map 100% of the assertion, you keep 100% of the assertion, you get 100% of the coverage, whatever those assertions, if you call it assertion coverage, whatever it is trying to cover, functionality or security vulnerability. But it turned out through different kind of scheme, the SS stands for signal selection, because I did not talk about, I talked about trace buffer, but in that trace buffer how the signals are selected, which one will be traced. If you do that smartly, then it is quite possible that even with mapping 60% of them, you can get a 100% coverage. 100% mapping 100% would give 100%, that is understood. Even 60% of assertions if you can keep, that would give you 100% coverage. And so, that would be if you do smartly. In fact, it can be even better, do better if you kind of focus on hard to detect events. So, if you are focusing some rare condition, hard to detect event and all that stuff, if you choose your coverage monitor from those areas, then it is going to be even more interesting. So, for example, if you have an assertion which is checking A, another assertion which is checking A and B, it is kind of little difficult to kind of figure out which one to keep, which one not to keep, unless you know that A is a very B is a rare variable. If you know B is a rare variable and A is kind of abundant, then you want to keep this one, then it is a rare event, this is not so rare. So, therefore, even when this one is getting activated, there is a high chance this also will get activated. So, if you kind of do which property kind of consumes the behavior functionality. So, functionally none of them covers any of them, but from a coverage point of view, think of inside a if statement which where if this is a straight line of code and if there is a if statement which has 2 branches, if you keep this one, all these portions are supposed to be covered anyway. So, you do not need to keep those assertions if you keep either this, but if you select this, you can't talk anything about this. So, there are those pros and cons. So, based on certain methods, if you do it right, then from 60% you can also reduce to 30%. Now, 30% is still large, but this is the kind of step some companies use. In fact, companies like IBM use this methodology not to keep in the final silicon, but something for acceleration. So, those of you kind of worked in the field of verification, you know there is this simulation, and then there is certain little more speed up is on acceleration, and then there is lot more speed up, 100x speed up on emulation. So, there are like Cadence, Palladium and all those $1,000,000 machines. If you buy, if you have a really large design, it takes time to map to it, but once you map to it, it really runs fast, very fast. You did not fabricate, you did not have the chip, you still have your VHDL, Verilog design, operating system, all of that, but you can run very fast. If you do simulate with real world applications, then it is going to take weeks or months to run one scenario, one test plan, one scenario. So, if you map it to the emulator, then what these companies do, they try to minimize the number of assertions they put on the emulator, because remember emulators run fast if you do not talk to them. If you talk to them, meaning emulators have to read something from keyboard or display something in the monitor, then it's think of it's like a breakpoint. It was running very fast, suddenly somebody running very fast, you said, can you slow down, take a cup of tea, just have one sip, you slowed that system down to produce certain event, consume certain event, then again starts running. That is why minimum number of IO would be ideal for emulation. So, it is not really the fabric. So, after emulation, when everything is fine, then they synthesize and then finally you have the chip. So, they do not keep on the final version, but they try to select a small set in the emulator version. So, depending on which company, what is their usage scenario, what market they are trying for, they try to keep certain variations of assertion. By a vast majority of companies get rid of all of them after pre-silicon. Any questions? Whoever wants to keep, they try to employ different strategies to reduce. How do I reduce? Which one are most important for me? What am I can live without, what I cannot live without? So, that is one way of minimizing assertion for using in an emulation environment or post silicon. The second one is, even if you map somebody in post silicon, because there is a dynamic circumstances, the way you use your phone, the way I use my phone is different, but when company produces it, they produce and optimize it for the average scenario. They have some average analysis. So, typically people make 20 calls a day, 100 text messages and all that stuff, but as you realize each of us usage scenario is totally different. I probably make 2 to 3 calls a day, text 4 to 5, and it is just me versus you. Even me versus me, maybe morning I do not use my phone at all, only in the evening. Maybe I do not use the phone at all during the week, only during weekends I call all my family members. So, the usage pattern of any device can change from people to people, from day to day, even within the day itself. So, then question is, what was customized or optimized for average scenario, that is probably not a beneficial way of utilizing power and all that stuff. So, that is the similar analogy applies for assertions. The assertions you mapped, all of those cannot be fired. Think about it, you have an FPGA fabric and you have a choice, and let us say you decided a small subset of 100 of them, but FPGA cannot map the bit stream. If you recall the way bit stream was mapped on FPGA, we cannot map all 100 of them at the same time, we can map let us say 5 of them. Then during run time, which 5 do I run? If I am making a call, maybe certain vulnerabilities are relevant. If I am texting, certain other vulnerabilities are relevant. If I am playing video game in my phone, certain other vulnerabilities are relevant, and it can change days, months and usage scenarios. So, then is it possible if I start with 100 vulnerabilities, remember the bit stream for these vulnerabilities are already there in the memory. The FPGA need to take it and put it in corresponding lookup table and map it, but because of the resource constraint it can, let us say, from 100 it can do 5, 10, whatever. How do I choose 5 from 100 while system is running? That is the problem of dynamic refinement. I want to distinguish what I talked earlier, that is a static selection. Statically you are deciding who supersedes whom and all that and done, that is a easy problem. This one is a much harder problem. Let me see if I can motivate that while you map it is a harder problem. So, now I am going to talk about dynamic refinement. This I talked little bit, but I made see little bit of it, but this synthesis, map, all that you just put it on the device, fabricated, and dynamic refinement is working while this chip is working in the system itself. And dynamic refinement is a common idea in any embedded device or many embedded devices in some form. So, the question is selection of profitable assertion and refinement. So, selection of profitable assertion, here is another way. I talked about the different way through signal selection and all that, but another way is there a way to cluster. Remember in unsupervised learning we had the notion of clustering. So, can we cluster a set of assertion and say they are kind of covering similar vulnerabilities? Once you cluster them, then can we talk about a dominator? If I in this cluster, if I trace or select or activate this assertion, then other assertions are kind of covered. It will not be covered exactly, but kind of covered. So, that is basically the story of clustering using unsupervised learning and selecting the dominator during runtime. But if you want to do dynamic refinement, the key problem is we have to solve this problem. What we are trying to solve? We are minimizing from that whole set S, we are trying to find a subset such that the power of that subset or whatever power it consumes below the power budget and the area below the area, there may be more constraint. And if I have to take some number, let us say in the system I have assertion A with kind of power profile, let us say 3 milliwatt area, forget about milliwatt and millimeter square, let us just put some number. There is assertion 2, let us just say this is 2, let us say the assertion 3, which is let us say 4, and let us just say this is 3, right. If my power budget is 5, then I can take, if I take A3 I can't take anything anymore, I am done, because it is already 4, none of the addition will make it 5. If I take A1, A2, then I am pretty much done, I can't take any more, but I still have to make sure if my area budget is 3, then I can't take these 2 either, right, depending on what is my area budget, what is my power budget. And then there is one more problem, let me see if I go forward I will come back, which is the problem would have been easier if this were, I will come back to this. So, problem would be easier if things were cumulative. So, what you are seeing in this diagram, the blue things are the kind of cumulative. So, for example, if I use 8 of the assertion, the power consumption should have been something like 0.07, but in reality it is 0.02. The reason being, when you do cumulative, you kind of think that when the design gets synthesized, it is like they are independently sitting in separate places, but you know how compilation work. If one of them is A and B, another is just A, probably the output of the A would be taken for the other assertion. It is not going to build another copy of A somewhere, A and B another. So, because of that optimization, actual power is not the cumulative one. If cumulative, it would have been wonderful. Because it is not that, because cumulative story does not work for neither for area nor for power, actual numbers are drastically different and you do not know that number until you implement it, synthesize it, map it, measure it, you actually do not know. If you do not know, then all these 100 situations you have, if you are going to choose 100, choose 5, that is an exponential number. 100, from 100 you are choosing 5 of them, 10 of them, whatever dynamically. You need to maintain a table of that exponential number table, all possible combinations of 5 and their area and power number. So, that dynamically some software can figure out which one do I choose and add, because otherwise it is not going to work. You cannot simply do cumulative addition of 5 of them to figure out if it is matching or not, because of that non-linear relationship. Let me go back to where I begin. So, it is basically a minimization problem. Basically, it is a minimization problem where you are basically trying to select a small subset from the all possible assertions that are already there in the FPGA memory, from FPGA memory. So, if this is you think of FPGA, remember we talked about it, we have this reconfigurable blocks, reconfigurable communication, and what I did not show you, there is FPGA memory, and from this FPGA memory, this bit stream or selected bit stream, a set of them will be pulled and mapped dynamically, 5 of them out of, let us say, list of this 100, 200, it is just a number, whatever number it is. That mapping process need to satisfy at least these 2 constraints. For example, it could be more constraint. It is a multi-objective optimization problem. So, this is the subset of the checkers, this is the cost function, this is the power function, and this is the area function, and this is the power constraint, this is the area constraint. Now, how do we, so cost calculation and so how to compute the function a, p and a, given that there are 2 to the power n possible inputs, because you have to try all possible kind of scenarios, and then optimization problem is, once we have this story, how to find the set that minimizes the cost while satisfies the constraints. And this we can use regression. If you recall the regression problem, the analogy I took, you are trying to predict the wind speed, not just whether it is a cat or dog, not the Boolean answer, not a classification. It is basically the regression problem. You are going to select a number, and for optimization problem it is a gradient descent. Remember that hill climbing, you are basically taking step function and going down. So, it is all machine learning concepts, and this is the of course, this involves model training, but the key idea here is that can I train a machine learning model which will tell me, if I choose these 3 assertions, how much area would be, instead of building an exponentially large table, doing exponential experiments offline before your device starts, and keeping a huge table in FPGA with different combinations, and FPGA will choose one of those combinations during runtime, which is kind of infeasible. We want to train the model, assuming model is tiny enough, and then we ask the model during runtime, if I choose this 5, tell me what would be my area and power. Now, of course, this has overhead of keeping the machine learning model itself, and the way people look at it, people kind of think, well, this there are many other applications people are keeping machine learning model anyway, it is all there, machine learning accelerator will make use of it or make use a similar version of it, right. So, cost prediction, as I said, you do take a subset, synthesis, simulate and train the regression model, this is the training part. And then, so here is a story I am trying to show you, for if you are going to choose 4 of them. Yes, please.
Why this assertion takes area?
Assertion is a function. So, whether you implement in software, it is going to be some assembly code. If you implement in hardware, it is going to take some area.
That's a condition check, right?
I mean, in programming language, assertion is implemented as a function call. When you say assert, file pointer, anything you say, this is a function call. I mean, conceptually this is if that function call, inside that if floating pointer equal to null, then you basically just print something, then you exit 0. But this is still a piece of code that will consume the implementation overhead, whether you see as a bit stream, whether see it as assembly, that would consume area.
But this must be negligible in context
if you map one assertion, yes, if you keep one assertion, and again remember the things are assert FP is a simple example. Most of the time the assert condition is actually complex and those variable would come from different places. If you map it in FPGA, that will come from different lookup table, lot of communication configuration, it would have a lot of overhead depending how they are placed. So, if you think of 4 kind of assertions, then there are, if you have 4 assertions and you are trying to take, there are different kind of scenarios. So, for example, if the scenario is we are going to take 3 of them and or maybe another 3 different 3, or it could be another 2 of them who will satisfy my requirement. So, there are many possible such scenario. For each of these scenario I need to compute the power and I need to compute the area, and if you want to, and all of that has to happen during run time. As I said, you can maintain a huge table or you ask the machine learning tool to predict these power and area numbers. Then your question becomes, if I have a trained machine learning tool, what is the overhead of that machine learning sitting in the FPGA and how accurate it is. That is all that boils down to. And so, then basically then when you solve the optimization problem using the assuming the machine learning can give me the numbers for the sequence, then I kind of choose which 5 do I choose, this 5, that 5, this 4, which one do I choose. For that if you recall gradient descent, you are simply basically from a mountain top, you are simply kind of, if you imagine you are just going down, that is the ideal situation. Every step you take you get closer to the valley, if that is your objective function, but in reality that may not be the case because of many other deviations, and every turn you might have multiple choices. So, most of the people what they use is gradient descent with simulated annealing, and the idea.
What is the actual, so earlier part I understand that you try to select a subset of the assertions which you want to check later, right, maybe
yes,
for emulations and all. But here you are also again try to select a subset of the assertions, but in which phase of your design
right.
process?
So, the emulation and all that stuff that could be done for even for post silicon, that you keep them and all of them. If I can keep executing all 100 of them, there is no problem. If I cannot afford, then 100 I know important and needed for post silicon, but I can't afford to run all 100 of them at the same time. That is the dynamic refinement problem. So, therefore, you have the bit stream or how to implement that information you have, but they are not active at this time, and the active area, let us say you can map only 5 of them. Then problem boils down to, based on my usage scenario of my device, which 5 do I choose at that time and map so that they monitor. If I am drinking a coffee in a public Wi-Fi area, then the vulnerability that is happening. If I am using my phone in my own home Wi-Fi, the attack surface is different. So, therefore, the situation is different, and if system is smart enough to take advantage of situation awareness, which 5 assertion it want to keep activated.
So, this 5 you are talking about will run on emulation or in post silicon?
It is post silicon, and this could be even for emulation, but we are saying is first let me just say first we have 1 million. So, 1 million let us say we reduce to 100. So, this is one story. Emulation, post silicon, if I can afford all 100 I will map. If I could have afford all 1 million, I could have mapped all million. Whatever subset I do, I can do that. Now, the scenario I am talking about, the subset I am trying to map, even I can't execute that. Then my question will be, okay, take 1 million and map 5. The problem with 5 is I could have done that, just take 5 and put it. Because the usage scenario changes, that 5 could be meaningless for many users. Meaningless where when they are accessing their phone in the airport or accessing the thing in their home. So, there is no dynamic reconfigurability. If you want to have that feature, then you basically you map more or keep more, but actually you activate only a subset of it. So, this is also subset selection, this is a dynamic or runtime, this is a dynamic one, this is a static one. Because it is dynamic, then I need to kind of figure out how do I select them?
So it is basically those 100 is already there inside
Already
your bit
there
stream.
in the FPGA memory.
In the bit stream.
In the bit stream format.
Okay. That means you have already implemented them, right?
You
So
already implemented them in the memory.
only just to reduce power consumption or maybe the timing, you try to select subset.
They are not mapped to the lookup table.
Okay.
So, where am I? Yeah, so gradient descent with simulated annealing. So, basically instead of the step function, it is basically kind of random feasible steps, and the way you want to visualize, let me. The way you want to visualize, typically if you think of any minimization function, this is classical from any optimization book. In any optimization book, if you want to do any minimization function, so depending on where you first started, you do not know where you started. So, if you started let us say here, then no matter what hill climbing you do, you are going to eventually go to this one. If you do normal gradient descent, you are going to get stuck here, because anything else you try, it is going to be a bad solution. So, when you do simulated annealing, you kind of do bunch of random jumps, you take some risk, but then you try. Remember, here we are not trying to get the maximum, we are trying to minimize the cost or any of those. So, then you are kind of you might have to do one more random jump, because here you can manually physically see it. When a solver is solving this, they do not see any of these values and things. So, somehow somewhere here there has to be a random jump, and then it needs to reach there as quickly as possible. Most of the time the solutions get stuck here. That is why people kind of combine. There is no guarantee, but simulated annealing will have that effect. That random jump is supposed to have, and research shows, and people usages. Now, so here are some results I just want to quickly show you. This I already talked about. So, cost prediction, how well does it predict the cost, and if you can see, most of the kind of there are some of the regression and linear regression with quadratic interactions. There are few machine learning models. As you can see, most of them, the prediction error, this is, think of this as an error, this has a big name, normalized root mean square, but think of this as a error. So, this error is really very small. Here it is little high, but you can still think of it is kind of less than 5% error. So, for so this is power consumption, this is area. Machine learning predicts when you select any set of thing, how much area or power it will take. That prediction accuracy is basically somewhere around 1% for power and kind of 5% for area. It is not great, but it is better than you just doing simple addition or maintaining exponential large table. So, there are for dynamic refinements, basically if, so for different benchmark, of course, story is different. If you really want to minimize your power, or so this particular case it is trying to do coverage, your coverage basically goes high if you can relax your power consumption. If you focus on any of the diagram, the power consumption, if you allow 0.135 milliwatt, you might be able to reach 100% coverage using even that small number of thing. But if you tighten your requirement, well, my system will not allow more than 0.115 milliwatt for the assertions itself, then the coverage boils down to, like, I do not know, I have to read this 3D, maybe like 40%, 30%, it drastically goes down, and that should not be surprising to you. More restrictive set the choices, so it would be able to map less number of assertion, it will have kind of less choice. But every design, if you can see this kind of portfolio where the so maximum LUT is the area, this axis is area, this axis is power, and this axis is how much coverage it can give you, your vulnerability coverage. So, that is why the dynamic refinement problem is an interesting problem, and it is academically definitely interesting, and it is hard to tell whether different companies are using it or employing it. Any questions?
This is only for FPGA.
So, ideally the question is it only for FPGA? I took the examples of FPGA, but dynamic refinement, as long as you have a reconfigurable fabric, and because today de facto reconfigurable fabric is FPGA, if there is any other reconfigurable fabric, it should work.
So, something cannot be done in software?
You can do it in software, but if the software speed is acceptable for the device in operation.
Only assertions, only for assertions. Anyway, assertion is a software functions.
Right, but
some part just can be put into software.
Right.
Because dynamically you are doing, and ASIC fabric may not allow to do, but can you do something in software?
So, the software, that basically means you have a set of functionality that running in software, and that software you have a set of assertion, you can selectively turn them on or selectively make the comment statement, you could do that. Which one you turn them? So, if you have a software program, so this idea is all same. If you have a set of program and you have assertion here, you have let us say 4 assertion, you want to activate only 2 of them. So, that boils down to this removing this comment line for 2 of them and keeping the comment line for the remaining
but
2.
For hardware maybe, but
after
you design
in the assembly, it is a commented assembly for 2 of them, which one you comment, which one you uncomment, that is basically you can decide based on the same gradient descent and those minimization algorithm dynamically if you want to decide.
My question is, once you fabricate the things, so you do not want actually any other reconfigurable fabric, but do it in software kind of thing. So, if you are designing for ASIC, what I can say RISC-V processor or some kind of processing environment.
Right. If you have a processor, then only possibility is the processor is running those assertions in parallel to whatever other hardware is running, whether it can do at speed interaction with the hardware devices, which is highly unlikely. So, just kind of to conclude this one, for assertion based validation, what I covered so far is basically it has 3 important components. Once I know the vulnerabilities, how do I automatically generate security assertions? Then how do I make sure those assertions are valid? And finally, can we use those assertions or a subset of those assertions in my post silicon environment like devices in deployment? And most of the work today, if you look, most of them are using large language models to generate assertions for capturing different types of vulnerabilities, either using large language models for detecting vulnerabilities or large language model for generating assertion and embedding them in the design automatically. In the next lecture, so today's lecture I am going to talk about firmware security verification, and I am going to make use of these assertions for designing, but the primary focus of this one would be firmware. What is firmware, where is it? We have some brief idea. Now, the question is how do we verify using some form of properties or assertions. So, we briefly talked about that any device you look at, if you zoom in, then basically it has a set of actuators, sensors and firmware basically between hardware and operating system. It is basically go between. It initializes the states and then it basically enables communication between hardware components and application software through operating system. That is basically its job. Now, when we try to verify firmware, it is kind of tricky, although if you look at it, hardware we kind of know, either it is fabricated chip or VHDL Verilog. Interestingly, firmware is nothing but C program or your favorite program in your favorite language. So, the first thing that will come to your mind, well, if it is software, then this is software verification. Answer is no, and I will try to give that flavor to you. It is actually not. Firmware is not a software, because software you can apply input and you can test it, firmware you cannot. You cannot apply input, because the kind of environment it operates, like the BIOS kind of thing, if you think of the kind of environment it operates, because of security requirements, the kind of constraints imposed on it, you actually cannot apply anything on it. Think of it provides some hooks that connects to hardware and talks. So, when you say, well, in that hook I will put some value, that is not going to work. It has to be you have to put it with the hardware, otherwise it is not going to work. So, the closest you can do, your C is running and VHDL Verilog is running together, that is the closest you can do. Because just applying some values to the software is not going to work, and also depending on the thing we will talk about it. But the key problem even in firmware verification boils down to same that we talked in formal verification, and you will see why in a moment. But let me explain to you this state space explosion problem, which is a problem for hardware verification, problem for formal verification, it is also a problem for firmware. So, in one clock cycle, if you know what needs to happen to firmware, it is working with hardware. If you unroll in 2 clock cycles, something happen. If you unroll for n clock cycle, it is a lot of space that need to consider. For a normal software, it is sequential logic. You can argue it has some state machine, but mostly sequential, things are simple. Once you make billion lines of code, it's sure it is complicated, but in firmware it has to deal with the complexity of the hardware. That is why let us talk about how do people do it today. So, this is basically how people do. There are 2 popular approaches, all the hundreds of papers that has been published, I can put it in 2 buckets. First bucket is manual abstraction. So, how the manual abstraction works? If you know what scenario for the firmware you want to check, then you take a version of that hardware run with the full firmware. So, this is the full code, full firmware, all of it, but this is not the full hardware. So, how would I say? Let us say your hardware is a processor, but this firmware or the interaction you are trying to check on the firmware deals with only adder. So, think of this is just a either think of add operation or just that adder implementation, that is it. Manually you abstracted, nobody did automatically, you manually abstracted, give the full firmware, give that adder functionality, and then that verification can be done. This could be multiplication, but this manual effort of kind of separating it, and there are a lot of work from Sharad Malik on instruction set abstraction level based thing. So, once you have a set of instruction set, you basically keep only the instructions or the part of the instruction set that is relevant for this particular scenario, whatever scenario you are trying to check. Remember, this scenario is same as assertion, it is same as behavior, same as property, but manual abstraction is the hardest part. If you do it wrong, everything is wrong. And as you realize, because it is in the abstraction level of instruction set, it does not understand pipelines, caches, branch prediction, it does not understand anything, but the actual firmware has to run on the real thing. So, you are not testing on real thing, you are testing on an abstract model. Even if it says it passes, there is no guarantee. On the other hand, people are saying, well, I mean, if this assertion scenario or this scenario is addition, all I have to tell the tool whichever solver, formal solver solving, I just have to say, well, do not focus on the whole design, just focus on the adder, and the tool would be able to figure out, okay, this portion is adder, so let me get rid of that automatically. So, it has to manually provide a hint. For every scenario you want to cover, you provide a hint, then the tool, internal formal verification tool, do the partitioning and get rid of everything else. So, this is equivalent story as this. Instead of manually giving this, during solving process, tool itself gets rid of the irrelevant stuff. So, that is you still have to provide that hint. Yes.
Sir, in this sir, the formal verification we have carried out.
Go ahead.
Sir, in this sir, like the formal verification that we learned previously, sir, that was being carried out pre-silicon. Now, sir, we are trying to abstract the hardware and then carrying out formal verification. So, formal verification we are carrying out on hardware post-silicon.
No, this is pre-silicon. Formal verification cannot be right. I keep saying hardware, this is think of a hardware model. In this particular case, this is not even Verilog code. This is simply instruction set. It is like add R1, R2, R3 or the functionality for that add functionality, that is all it is. That is why I drawn that diagram and said this part of the code VHDL Verilog code. You manually abstract or you give a hint which will do the abstraction for you, right. So, if you give hint, then you can take the full firmware and you can take the full hardware, that is a good news, right. So, yes please.
I have a question.
Yeah.
Sir, like whatever firmware we will take, that firmware is only for either or it will be for the whole system basically.
So, I am trying to focus the problems, but firmware is for the whole system. So, in the car example, firmware is supposed to initialize different actuators, different sensors, read data from sensors, of course, with help of other people, but this is the sole responsibility. Whatever operating look from hardware perspective, that is basically firmware.
Yes.
Firmware is the operating system if you are looking from the hardware side. If you are looking from the program side, that is really operating system, which is basically scheduling which program will run, who will stop, how will context switch, what will happen. Applications do not see firmware, but firmware's job is to initialize different control register, setting separate bits, communicating data, transferring things, taking care of everything. It is the operating system from, and it also does lot of other things. Whenever you design the system first time, the BIOS, that is the area where it sits. Whenever you buy and you want to install the Windows, whether you do, sysadmin does it on your behalf, that BIOS checks all these stuff. Is it a legitimate operating system? Should I execute it? Is it compatible and backward compatible with the previous one? Can I do rollback? It controls all of that. And the worst part is, it has to take care of itself also. If somebody is saying BIOS need to be upgraded, before upgrading itself, it need to check its health, the health of the person coming in, because if somebody coming in and replacing me, I need to make sure whoever is coming in and this superpower actually trustworthy. So, this firmware upgrade, anti rollback, it has a lot of functionalities which is not natural for any software program. You think of bubble sort, insertion sort, average computation, Fibonacci series, that is not they do. Check your health, check others' health, allow upgrade, decline upgrade, all of that it needs to do. It is an extremely secure environment. It is more secure, more privileged than operating system. So, now there are a lot of stuff that can be done. I will just touch upon some key ideas to kind of show how can we do hardware firmware thing without doing abstraction. Like the way concolic testing did, we actually tried to do it is not concolic testing, it is a verification hardware firmware security co-verification framework that we can do. Or if you think of the previous example, can I automatically generate hints? So, this whole scalability issue, when you have a lot of hardware, how do I take care? What is the key idea is, based on the formal verification ideas I gave in the morning, you will be able to understand at least in some layman terms. So, when you have an implementation and you have a specification, you manually you construct some formal version of them and you try to check are they equivalent. But the thing is, because you are operating on the abstracted model, even if it says equivalent, you do not know if that is true. But the only good news is, if they say there is a failure, that is valid, otherwise nobody will use such approach. If they say it is successful, that does not guarantee it is completely successful, but if it finds a counter example, that counter example is valid on the original design. That is the good news. What we are basically saying, if you want to do on the actual design, can I break down the from full system to module level? Even within each module, think of a processor as fetch, decode, execute. Can I just solve the problem on the decode? Even within decode, can we just solve based on scenario? What are these scenarios? Remember this assertion? Assertion is checking one of the scenario. So, can we check for one of the scenarios? So, then if you think of slicing, first you reduce complexity at the component level, then you reduce scenario at the abstraction level. Now, then you put the symbolic execution. So, for example, if in a calculator if you want to kind of verify all possible scenario, it's really a lot. But if I tell you, well, can you check the only add operation for me please, then you are basically trying to figure out which path to check, then it kind of becomes tractable. Now, this scenario based, so at least this tool is also Hive is also open source, you can play with it. So, the scenario, the good news is this system does not know anything. You give it a scenario, you say 2 plus 3 equal to 5, you give just this scenario. One operation you tell the system will figure it out that I need to verify add. What is the difference between this and a, so this seems like a test case and it may seem like, well, then what is the advantage, how is it a formal verification? If you give a scenario of add, this system will check 2 to the power 128 possible scenarios for the adder. It did not cover all possible scenarios, it did not give you a guarantee, but it gave you a guarantee all possible additions it will check for you through symbolic execution, but you have to provide scenario. If you do not give scenario, so then problem, still the research problem we want to pursue, how do I create different scenarios. So, if you give add, it checks all the possible additions. If you give multiply, you still have to know what operations that system support, what are the scenarios you want to check. Then this scenario level decomposition and verification, that basically becomes an important story for firmware and hardware. And recall, firmware has to run with hardware. Independent verification of firmware has no meaning, it does not even make sense. Now, another way to visualize where we are getting advantage, let us say from input of the story to output, there are lot of modules are involved, lot of state machine transitions are involved. If I tell you a scenario, maybe only 1 or 2 of the paths are relevant, you are basically telling your solver, constraint solver, please focus on that path. That is what our teachers, our parents tell us, please do not look at left, look at right, all that attraction, materialistic world attraction, stay away from them. You are basically focusing, if you are focusing on solving addition, you just focus on addition, you do not focus on other scenarios while you are solving the problem. So, if you can think about it, during solving time it is actually doing the slicing, auto slicing. So, I just wanted to show quickly too before I for solving this problem full blown, there is an assumption I did not tell you, which is this is applied to IoT devices. So, IoT devices such as this backup. So, it is a full system, because remember firmware verification is meaningless unless it is in the full system mode. So, this is a RISC-V CPU, some RAM, some ROM, an external flash hard disk, and this driver, flash, cipher and all that, and all of it can be fully formally verified with the firmware. So, same thing, but if you do not do this kind of approach even for such a simple system, first of all RISC-V, if you look at it, it is really large amount of code. Then this one is elliptic curve cryptography. The day I discuss the cryptography, you will get better idea. This is RISC-V, elliptic curve cryptography accelerator, and then ROM, which has the firmware, and different type of elliptic curve cryptography arithmetic, SA. This is basically their authentication, ECDSA and ECIES. So, that is another module. This one is liquid crystal display controller, again similar thing, only difference is the different types of drivers or the drivers that firmware interacts with. Remember, whatever external device you put in, they will have driver. For that device, from that device perspective, that driver is the operating system. From hardware perspective, this firmware is the operating system, and by the way, these devices there is no actual operating system. There is no actual operating system, because the applications that they are running, that is pretty much it. Same thing we have done for the serial advanced technology SATA controller, and again it is all the different media, different storage, and how do you connect the cable, and that is kind of the scenario. And that is pretty much all I have for today. If you have any questions, I will be happy to answer.
So, is this firmware codes are available publicly?
Firmware codes are publicly available, at least for majority of the devices. Public, RISC-V based devices firmware codes are available.
Those are basically the BIOS, whatever they are research in BIOS.
Those are the BIOS and written in some variation of C or some variations of C programming language. The things that I did not talk about, so verification of this firmware, because you can't apply for primary input from hardware or through other interactions, you have to activate certain functionality or assertion, and if you try activating from the input, then it would be state space explosion. Instead what we do, whatever you want to activate, we start from there. So, if I draw pictorially, if this is your firmware, if you think this is an entry point, and if you try to reach a, there are different function call, different assertion, if you try to go from here, there would be state space explosion. Instead, if you start from here and keep going, remember you do not have to come to entry point, because the way firmware works with hardware, this could be the boundary itself, interaction boundary with hardware. So, you start from actually what you want to activate and then keep going until you find some interaction point with the hardware, and then that is how you verify. Then you figure out what needs to happen in hardware for this precondition to happen. You start from the actual target point, then from the entry point of the firmware and try to reach a state space explosion, and that is one of the reason nobody works in firmware verification. Any other questions? Thank you.